Hello class, I wanted to go over the rest of the problem that we talked about on Friday in class. So I'm going to go through question A or question 3A, I should say. And what we want to do in that is find what the probability is of a man being overweight based on his BMI, which means that the man has a BMI between 25 kilograms per meter squared and 30 kilograms per meter squared. The probability is going to be based on this model up here. And so we want to know in the year 2000. And since we want to know in the year 2000, we've already in class said that x can take on values of 1 if it is 2014 and 0 if the year is 2000. So that means that we know that our model is yi equals 27.7 plus 1.1 times 0 plus EI. And we also know that EI is distributed. Remember, this little tilde means distributed. Normally, the n means normally. And the errors have a mean of 0. And our standard deviation is expressed as 0.97 kilograms per meter squared, which we get from right here in the equation. Okay, let's start off by drawing our graph. So we're going to draw a graph. And we can look at this model and say that since this is 0, this cancels out. So effectively what we're looking at is a single Gaussian curve with a mean in the middle here at 27.7. And we want to know the probability that a man is between 25 and 30 kilograms per meter squared. So we want to get the area, the probability in this area here. That is our ultimate goal. Now, you'll notice that from what we've talked about before, we haven't really talked about how to necessarily get just this middle here when the two sides aren't equally distant from the mean. And in this case, they're just slightly off. 25 is 2.7 kilograms per meter squared away from the mean, while 30 kilograms per meter squared is 2.3. So they're not symmetrical. So what we're going to need to do is we are going to need to think about this in the process of two different probabilities. The first probability is to find, so let's draw in our 27 here, 0.7, and we'll draw in our 30 here. The first probability that we're going to need to find is the probability that a man is less than 30 kilograms per meter squared. So that gives us our first boundary. And then once we have that, we're going to need to subtract out the probability associated with this white space over here. This white space over here is not included in our probability. So what we're going to need to do is subtract it from this orange part here. So to do that, we're going to take this green marker and we're going to subtract out anything that falls on this side of 25. Now expressed this way, it should become clear how one might go about doing this. So we want to find the probability that yi is is less than 30. And we can do that based on everything we've already learned, right? Our best guess of our model, now that we've canceled out this part, is 0. Now that we've canceled out this part 0, our best guess is 27.7. And so now we need to find the error associated with 30, right? So we can say that the error we care, so we're going to say that, and remember our error is the error of the model. So our model says that we have 27.7 kilograms per meter squared as our best guess, but what we're looking for is the value at 30. So our error, actually we're going to make a star for this because we're looking for a particular value. So our value, as we mentioned before, is 2.3. Now this is expressed in units of kilograms per meter squared, right? But in order to get the probability, we need to get the probability that y in standard deviations where y equals 30. And so we know that one standard deviation equals 0.97 kilograms per meter squared per standard deviation. Now that's all very confusing because that's a lot of fractions and it's a little bit hard to see. So let me try to refocus the camera here. So that's all very confusing, but you can just think of this as the units of measurement, right? And we have right now 2.3 kilograms per meter squared. So we're going to divide those because kilograms per meter squared is on the top for both of those. So we're going to divide by, we're going to take 2.3, which is the error associated with this right bar. We're going to divide by 0.97. And again, remember, let's write this out in a different way. Let's say 2.3 kilograms per meter squared over standard deviation. I'm sorry, 2.3 divided by 0.97 kilograms per meter squared over the standard deviation. Because we're dividing, these will cancel, and we will end up with, all right, and after checking my calculations, I get that this equals the 2.3 kilograms per meter squared times 0.97 equals 2.37 standard deviations. So this is the value in standard deviations. We want the probability of that. So we're going to take the value from our p norm of 2.37 equals, and I'm just typing it into R now, 0.99. So that means that our orange values here, the value from here to here, covers 99% of the distribution. Now we need to do the same thing for the green values. And the green values, we use the value of 25. So 25 minus 27.7 is this time our standard error. I'm sorry, our not standard error, our error. And that equals 2.7. Negative 2.7, excuse me, negative 2.7. So when we divide negative 2.7 by our standard deviation of 0.97, we get negative 2.78. We figure out the probability of that. The probability of p norm is 0.002 or 0.003%. We'll add the decimal on up here to 1. So in order to get, so now we need to subtract out this green value. So this orange value here is the probability of being in the orange. This value here is the probability of being in the green. We need to subtract the green from the orange, so we take 0.991 minus 0.003, and the value is 98.8%. And that's the answer. And in class, I'll explain why this answer, as Alessandra suggested, doesn't make much sense, but I will do that in class on Tuesday. But this should be the answer given the information that you were given. Alrighty, have a great rest of the weekend, and I will see you on Tuesday morning.